everyone, welcome back. In this video, I am going to discuss Cambridge IGCSE Physics, Paper 6, May, June 2024, Paper 62. So please stay tuned until the end of the video because I'll be giving you a lot of tricks, a lot of tips, right, along with the discussion. Are you ready? Let us get started. Now, let us look at the first question first. A student measures the spring constant K of a spring by two different methods. The spring constant K of a spring is a measure of how difficult the spring is to stretch. Method number one, A, the student attaches the spring to a clamp as shown in Fig 1.1. This is Fig 1.1 and suspends the mass M equal to 500 grams from the spring, pulls the mass down a small distance and release it, let go of it. The mass will oscillate up and down. And the student measures the time t taken for 20 oscillations of the mass. Reading on the stopwatch is shown in Fig 1.2. Record t in table 1.1. Okay, this is a t. 17.76 second is the value of the t. So I am going to write here 17.76 is the value of the time for 20 oscillation. Now, the second part, the period t of the oscillations is the time taken for one oscillation. Calculate the period t of the oscillations. Record your answer in table 1.1. T, which is a period, can be calculated by the total number, okay, or the total time for 20 oscillation divided by 20 number of oscillation. So in this case, I got 0.888 second. Remember, period must be denoted with 3 significant figures. So you have to be careful with that. Now, the next one, B, suggests how the procedure can be improved to increase the accuracy of the result. I say that because you look at the table given, the student just conduct the experiment once and find the value of t right away, right? I say that maybe first, maybe you could increase the number of oscillation and then repeat the experiment 3 times and find the average for better accuracy of the result. So I say take, or you can say take more, or you can say, okay, take more oscillations and repeat the experiment. Don't just repeat. And average, find the average. That's it. C, calculate a value of K1 for the spring constant of the spring. Use the equation shown. K1 is equal to 19.7 divided by T squared. So I'm going to use 19.7. T squared is 0.888, but you have to square it. Capital T represents period. And I got 24.98 Newton per meter. So I'm going to round it off to 25, 2 significant figures. Method number 2. The student measures the stretch length L of the spring with the 500 gram mass still attached. In centimeters to the nearest 0.1 cm, Fig 1.3 shows the stretch spring drawn to a scale of 1/4 full size. Right. Now, first part, the length L of the spring is the distance between the dotted lines in Fig 1.3. Measure L. All you need to do is just to take out your cm rule like this and place on the 2 dots to measure the length of the spring. The length that I got was 5.6 cm. And the second part, calculate the actual stretch length of the spring. Remember what the question told us, that this is just 1/4 of the full size. So if you want the real, right, reading of the length, you should do it as 5.6 cm is just equal to 1/4 of the real length. So the real length should be 5.6 cm times 4, which is equal to 22.4 cm. 22.4 cm is the answer. Record L in table 1.2. So I'm going to put it as 22.4. E, the student removes the 100-gram masses from the mass hanger one at a time and repeats the procedure for masses of M equal to 400 grams, 300 grams, 200 grams, and 100 grams. The student records each value of L in table 1.2. Now, the first part, plot a graph of L in cm on your y-axis and M in gram on your x-axis. Start your axis at the origin, 0, 0. So you have no choice but to start from 0, 0. Draw the best fit line. So for x-axis, my scale is 100, 200, 300, 400, and 500. So I don't have to label my x-axis and y-axis because this question already labeled for me, thank God, right? So for y-axis, I start with 5, 10, 15, 20, 25. Now, okay, I put all the values here, right? When M is equal, x-axis is equal to 500 grams, the L or y-axis is equal to 22.4, which is here, Yeah. So when the x-axis is equal to 400, it is 18.3. I put it here. When the x-axis is equal to 300, y-axis is 14.3, which is here. And when x-axis is 200, y-axis is 10, exact 10. That is good. And when the x-axis is 100, the y-axis is 6.1, which is here. And I draw the best fit line, which crosses most of the points. Now, the second part, calculate the gradient G of your line, show all your working and indicate on the graph the values you use. So you have to show your coordinates. Remember, how do we calculate gradient? It is actually from math. Y2 minus Y1 divided by X2 minus X1. So we have to label the two coordinates. You need at least two coordinates to calculate your gradient. And whenever they ask you to show all the working, you need to draw the triangle of how you measure your gradient, right? How you calculate your gradient. I mean, the triangle that you draw must occupy at least half of the straight line graph. Remember, the straight line graph, you measure the length of the straight line graph, must occupy at least half of that length. So my gradient would be y2, which is 25. Y1 is 4 minus X2, which is 507, X1, which is 50. And I calculated, and I got 25 minus 4 divided by 507 minus 50. The answer that I got was 0.046. So 0.046 is my answer. Now, the third one, an estimated value K2 for the spring constant of the spring can be calculated using the equation K2 is equal to 1 over G, 1 over gradient. You calculate K2 using your value of G from E part 2 and the equation shown. Now, I'm going to do the calculation. K2 is equal to 1 over 0.046. I got 21.76 or 21.8 Newton per meter. 21.8 Newton per meter, that's my answer. 1 over G, yes. Now, you just recalculate that. Just make sure that I get the correct value, 0.046, and I got 21.8, yes. Now, F, the two quantities can be considered to be equal within the limits of experimental accuracy if the values are within 10% of each. Compare your values of K1 from C and K2 from E part 3. State whether your results indicate that the values can be considered to be equal. Support your statement with a calculation. So I write down the value for K1. Write down the value for K2 first. K2, I got 21.8. Newton per meter, and my K1, which is 25. My K1 is 25. So I'm going to put 25 Newton per meter. Now, to calculate whether the values are within the experimental limits of experimental accuracy, you know what I'm going to do? I'm going to calculate the percentage of K values, right? How do you calculate the percentage of K value? I want you to listen carefully. You take the larger K value, take the difference between the two K value, divided by the smaller K value, which is 21.8, and you times 100%. So I'm going to do it. 25 minus 21.8. By the way, if you want to round it off to 22, it's not a problem. Divide 21.8 times 100%. And I got 14, okay? 14.67, which I'm going to round it off to 15%. 5% more than the limits of experimental accuracy, right? So this is how I'm going to answer. Since percentage of K value is equal to 15%, which is larger than the limit of experimental accuracy, which is 10%. Hence, the result cannot. Okay, the result of K values cannot be considered to be equal. So sorry. So that's the answer. Now, question number 2. A student investigates the resistance R of a diode using the circuit shown in Fig 2.1. A, the student closes the switch, records the voltmeter reading. V, records the ammeter reading. I, and open the switch after that. Fig 2.2 shows the readings on the voltmeter and the ammeter. Record the readings on the voltmeter and the ammeter in the first row of table 2.1. But before that, I have to take reading from here. Voltmeter reading is 0.5. This is 0.6, 0.7, 0.8. 8.2, 8.4. Voltmeter reading is 0.84 volt. I just put it here first. And the ammeter reading 0.1, 0.2, 0.3, 0.3234, and 0.36, 0.36 ampere. Here's the reading from the ammeter. I'm going to fill in the blank here. So this is 0.84. This is 0.36. That's it. B, calculate the resistance R of the diode using your meter readings from A. Use the equation. They're so very kind. Use the equation R is equal to V over I. So for this R, how do you get the value? You just take V value, which is 0.84 divided by 0.36. And I got 2.3. I put it in terms of two significant figures because my V value has two significant figures and my I value has two significant figures. Now, the next one, this is V, which is equal to 0.83 divided by I, which is 0.27, and I got 3.1. And the last part, okay, this blank, I have to fill in the value of current. I is equal to cross multiply from here. It is V over R. So 0.81 divided by 4.5, and I got 0.18. As the value of I. And record your answer in the first row of table 2.1 to an appropriate number of significant figures. I did that. I put two significant figures because my raw data have two significant figures. C, the student connects a 3 ohm resistor in series with the 10 ohm resistor between terminals X and Y as shown in Fig 2.3 and repeats the procedure in part A. Oh, okay. And connects the 7 ohm, 10 ohm, and 3 ohm. Added more resistors in series between X and Y as shown in Fig 2.4 and repeats the procedure in A. Okay. And table 2.1 is incomplete. Complete table 2.1 by adding the missing values of R and I. I already did that. D, as the resistance between terminals X and Y is increased, the current in the circuit changes. Use your result in table 2.1 to state the relationship between the current and in the circuit and first part, potential difference PD across the diode. Let me see. What happens when the current resistance, okay, so you look at the value of the resistance, it is increasing. What happened to the values of the current? It is decreasing from 0.36, decreases to 0.27, decreases to 0.18. So I say that as the current, oh, I have to talk about, okay, the current. So when the current is decreasing, right, what happens to the potential difference across the diode? So this is the diode. When the current is decreasing, the potential difference across the diode will also decrease, right? So you can see that the potential difference across the diode, yeah, because of potential difference across the resistor, right? It is from here. Okay, now we are just comparing the potential difference. That is why I say the potential difference due to the current that is decreasing. Current decreases. I focus on diode. PD, I can use the short one, PD, in short, right? Instead of writing the full sentence, potential difference, I can use PD because the question explains the symbol. Yeah, the short one. So PD decreases. Second part, the resistance R of the diode, right? What happened to the resistance of the diode? I would say that the resistance, since the current decreases, right? You can see the value of the current decreases. So the resistance of the diode, okay, current decreases, R increases. Because remember, current and resistance, they are enemy, right? When one is increasing, the other one will decrease. E, a student attempts to set up the circuit shown in Fig 2.1. The student finds that the ammeter does not give a reading when the circuit is complete. The ammeter is not broken, such as why the student may have done incorrectly while setting up the circuit. I would say that, do you still remember the function of a diode? I'm going to focus on this diode only. The function of the diode is to allow the current to flow in one direction only. So even though the circuit is completed, but if the diode does not allow the current to flow through it due to diode is being connected in reverse bias, right? The current would never ever flow through it. So that is why I say one of the possibility is that diode is in reverse bias. Now, F, name a single device that can be used to control the current in the circuit instead of adding extra resistors in series, right? Draw the electrical symbol for the device. You know, when we have technology nowadays, right? So that name of the device is called variable resistor, or you can call it as rheostat. It consists of the resistant wire. Yeah, a coil of a resistant wire. So you just use a slider to slide left or right. You can increase or decreases the resistance as you wish. So the electrical symbol is the rectangular shape with the two hands like this, and then arrow pointing upwards because you want to change it. So that's the symbol. Question number 3. A student investigates the deviation of a ray of light passing through a transparent block ABCD and measures a quantity called the refractive index N of the block. A, the student's ray trace sheet is shown full size in Fig 3.1. Now, first part. On Fig 3.1, draw a normal at the point E. Extend the normal above AB and below CD. Label the upper end of the normal with the letter N, the lower end of the normal with the letter M, and the point where the normal crosses side CD of the block with the letter G. Wow, so many information that I have to digest here. Therefore, I'm going to use my ruler again. Okay, so normal is a vertical line, which is 90 degrees to the surface of the block. So normal must be denoted with the dashed line. Remember, so I have to extend beyond CD, beyond AB. And then, okay, keep the ruler first. Label, okay. Label the upper end of the normal as N. N, okay, this is N. And the lower end of the normal as M. And then the one that crosses CD is G. Done for the first part. Measure the angle between the lines FE and EN. This is your FE. This is your EN. All you need to do just to use your protractor to place your protractor here. This one, okay, I got it as 60 degrees. Right? The answer that I got from my protractor is 60 degrees. So the answer that could be accepted is 59 degrees to 61 degrees. The range is quite small. So you have to make sure that you measure it as accurately as possible. B, the student positions an illuminated slit on the ray trace sheet so that a ray of light passes along line FE towards E, marks and labels with small crosses X 2 points on the ray that leaves side CD of the block. Removes the transparent block. On Fig 3.1, extend the line FE until it meets the right-hand edge of the ray trace sheet FE. I have to extend it, so I have to use a ruler to draw it. Okay, now I try to bend my ruler. Okay. Okay, make sure that, okay, if you draw on a piece of paper, that will be more accurate as compared to me drawing digitally. Okay, will be not so accurate as compared to yours, yeah? So I'm going to draw it. Okay, this is a 1. Okay, done. And then they asked me to label as Z. So this is Z right here. Done. And then after that, label the end of this line as C. Draw a straight line through 2 crosses to meet side CD of the block. Okay, these are the 2 crosses, so I have to draw a line. Okay, to meet CD. Now this is a line. I'm going to draw. This is it. And then keep the ruler. Right, meet CD, and then you have to meet CD of the block, label the point where the line meets CD with the letter H. So this is it. Okay, H is here. And after that, done. Label the other end of the line with the letter J. Okay, this is J. And done with that as well. Draw a straight line from E to H. Where is E? Where? Oh, okay. From E to H. Straight line from, okay. Try my best. Still trying. Okay, my answer might not be very accurate, right? Because I draw it digitally. So I hope you can understand. This is just a method, a guide on how to do it. If you draw it on a piece of paper, that would be more accurate. This is the line that I drew. Measure the length L of EH. Just place your ruler between E and H. You just need to measure the length. The length that I got was 7.4 cm. So I just put it here, 7.4 cm. And measure the perpendicular distance D between HJ and FZ. So this is FZ, HJ is this. So perpendicular distance, you know how I do it? Okay, this is how I do it. Okay. Make sure that, yeah, I just want to guide you on how I do it. Use your protractor, okay? Just measure between these two, okay? Because there are, okay, this is the length that you are supposed to measure. I put it in blue, okay? This is it. Sorry. Make sure that you use your protractor to measure. Okay, I keep my ruler first. Let me tell you how to do it. This one must be 90 degrees. This one must be 90 degrees. Okay, So 90 degrees between these two lines. Okay, not this one actually. Okay, wait, I will redo this. Up. This is the one. Okay, the ruler must be between these two lines. Like that. So these are, okay. And then I keep my ruler. Okay, make sure that this is 90 degrees, this is 90 degrees. This is the length that you're supposed to measure. This is it. So I got my answer. I think 2.8 was my answer. Right, let me write it down. I got 2.8 cm. And calculate D over L. D is 2.8 cm. L is 7.4 cm. I got 0.38. There's no unit for D over L because cm and cm can be cancelled out. Right. Then, just want to tell you what's stated on the mark scheme. The L value must be within 7.4 cm to 7.6 cm, whereas the value of D that you measure must be within 2.8 to 3.2 cm. Right? Now, D, the measurement of the quantity, is reproducible if a similar result is obtained when the measurement is repeated by a different method or under different conditions, such as how the student can adapt this experiment to check if the value of D over L is reproducible. I say maybe the students can repeat on the other side of the block, right? With the same exact angle that I measured initially, which is 60 degrees, and to see whether D over L, yeah, you will get back the same 0.28, 0.38 in my case. Student can repeat the experiment on the other side of the block with same angle of 60 degrees. I got 60 degrees. You might get like 59 degrees. You might use that. Right. E suggests one source of inaccuracy in this experiment, even if it is carried out very carefully. When they say very carefully, there's no parallax error. Right? You cannot talk about the parallax error. So I have to scroll up again to see what could have done wrong. Okay, first of all, they only tell you deviation of the ray of light. The question did not stated the size of the ray, the thickness of the ray. So the ray could be kind of like thick, but if you want your experiment to be more accurate, a beam, a fine beam must be used instead, right? So I would say that maybe the beam of light, right? Okay, beam of light ray, which is not fine enough. It is not a fine beam. You're supposed to use a fine beam in order for you to get very accurate result. Now, F1, measure the length L of GH. Length L of GH. This is the length that you are supposed to measure. Okay, just place your ruler horizontally. Then you will get the length L. So the length L that I got was 4.3 cm. And then this F2, use the value of L from C part 1 and L from F part 1 to calculate a value of N, refractive index, for the refractive index of the block. Use the equation shown. So N is equal to 0.866 times the L I calculated from C part 1. Where's the L? Which is 7.4. Okay, going to use that. 7.4 divided by 4.3. And the N that I got was 1.49. There's no unit of N. Refractive index has no unit. Range given in the mark scheme is between 1.40 to 1.65. Quite a large range. Right? So now we can move on to my favorite part of the question in paper 6. Which is question number 4, the last part of paper 6. Because you know why? Because I can be a planner. I can instruct the students to do this and that, right? Don't you feel excited as well? Now, question number 4. A student sets up a flexible track at the edge of a bench. Student investigates the metal ball as it rolls from rest down the track and it travels through the air. The metal ball travels a horizontal distance d through the air and lands in a tray of sand placed on the floor. Plan an experiment to investigate how one variable affects the size of this distance d. Right? The apparatus available includes flexible track, how long you want it to be, clamp, balls, and stand to support the track. Okay. Selection of metal balls. So metal balls with different sizes, different masses, right? Fig 4.1 shows how the flexible track is supported. In your plan, state one variable you have chosen to investigate. I actually choose, okay, the variable chosen. I choose mass of the metal balls because they gave me a selection of the metal balls. So I choose masses of metal or mass of metal balls, sorry. Mass of metal ball. That is a variable that could affect the D. Now I've done with the first part, so I put a tick here. List any additional apparatus needed to measure this variable. So I'm going to list it right now. The additional apparatus that I need is definitely additional apparatus that I need would be electronic balance because I want to measure the mass, electronic balance. And I also need meter rule because I want to measure the distance D. Don't you think so? And I'm done with that. Explain the third one, explain how to do the experiment. That is the method. So I'll just write down the method here. First of all, I would say that first, mass of metal ball is measured by electronic balance. Okay, and then ball is rolled on flexible track until it falls and lands in the tray of sand. Full stop. Third, meter rule is used to measure distance D. And don't just stop right there because you have to repeat the experiment. Experiment is repeated with different masses of metal balls. I'm done. I'm done with the method part and I put a tick here. And the next one, state the key variables to be kept constant. What are the key variables? Variables means plural. So I will just write down here, variables to be kept constant, or you call it as control variable. They are just variables. It's just that during this experiment, you want to keep them constant, right? I say maybe length of the flexible track, maybe the size of ball, and maybe the starting point of metal ball on the flexible track, right? So I'm done with that. And the next one is I have to draw a table, right? So the table would be, this is my table. So my table would be mass, which is measured in gram. Oh, I don't just put mass. Mass of what? I have to explain. Mass of metal ball, which is in gram. And my other one will be distance D. So this is the table. Done with the table part. I do not have to fill in the blank because I don't know. I'm just a planner. And explain how to use the readings to reach a conclusion. So my conclusion is that the easiest way is to plot a graph of mass of metal ball against D to see the relationship. That's all for May, June 2024, paper 62. I hope you gain benefits from this paper and I wish you all the best in your paper 6. So if you have any hesitation, any doubts or any question, do comment below. See you in my next video. Bye.